Bismillahirrahmanirrahim. So in this lecture we are going to continue with where we left at the end of the last session before mid. We were talking about relational algebra. We discussed certain parts of it, but there are other parts that are remaining, particularly about the joins. So in the next two slides I will just recall what we did so that it becomes fresh in your memory, and then we are going to move to the next part of this lecture. So if you recall, what we did was that we discussed about the unary selection, we discussed about the projection. So in the unary selection, what we do is we use this sigma notation, and where we have the condition and R is the table or the relation on which we are applying this operator. So if you apply the sigma operator on the relation R, and so if this is the relation and this is the name, this table belongs to the person, and we have three different attributes and three data instances there. So if you write, if select age from person where age is equal to weight, so select, in fact select asterisk from person where age equal to weight. You are using the filtering where age equal to weight. So the only case where age equal to weight is this. So this is 54 and this is 54. So only this row will be selected. So you are filtering on the rows and not on the columns. For the projection, you are filtering on the columns and not necessarily the rows. So if you project on the age of a person, so only this column is projected, age 28, 29, 54 and 34. This will be displayed. Then we have three other operators. Then we have the union operator, the intersection operator and the set difference operator. In the union operator, which we denote as R union S, it includes all the rows that are either in R or in S or in both, where R and S are the two relations of the two tables. The intersection, denoted with this symbol, includes only those rows that are both in R and S. So it cannot include a row that belongs to only one of the table. So the rows have to be in both these tables. Then we have the set or the difference, set difference operator or the minus operator, and it's denoted by the minus sign. And if we say R minus S, this includes all the rows or the tuples that are in R but that are not in S. So it's a simple minus operator. Next, we discussed last time the Cartesian product, and we said that it is a cross product. A cross product means all values from one set are paired with all values from the other set. So it is denoted with this cross or the multiplication symbol, and it's a binary set operation, but the relation on which it applies do not have to be union compatible. So as opposed to a union, in this case it does not have to be union compatible. So R cross S defines a relation that is a concatenation of every tuple of the relation R with every tuple of relation S. So the degree of that resulting table, so the degree is the number of columns. The number of columns of R cross S is the degree of R plus the degree of S. In simpler words, the columns of the table R plus the columns of the table S, even if some of them are redundant. So you are just going to add them. If there is a common attribute, it will be repeated. The cardinality is the length of the table in terms of number of rows. So the length or the cardinality of R cross S is going to be the cardinality of R cross the cardinality of X. And so you have a multiplication. That is why it's called the cross product. So the Cartesian product is the cross product, because the number of rows are going to be the multiplication of the number of rows in each of the individual tables. So for instance, if we have this example, so in this case we see that if we look at the employee table, and we look at the department table, in this case if we take the first example or the first row, so John Smith has a salary of 30,000 and works in department number 5. So John Smith works in department 5. Normally, if I want to combine these two tables, for instance, I want to know which department number 5. What's department number 5? I want to know the name of that department. So I can combine this and it should give me, perhaps here I can find that department number 5 is actually the research department. However, if I am doing a Cartesian product, this means that this row is going to multiply with all the other rows. So we are going to have this combination, we are going to have this combination, and we are going to have this combination. So because of this row, we are going to have 3 new rows. Then we go to the second one, it also combines with all of them. So 3 new rows for the second row, and so on. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 rows here. It means the resulting table is going to have 8 multiplied by 3 equal to 24 new rows in the table. And some of them may or may not make sense. For instance, we have John Smith, 30,000 salary, department number 5. When it combines with department number 5, we know that it is research. Now this makes sense. However, in some cases, for instance, when this row combines with the admin department, department number 4, then it results in this value. Now this is department number 4, this is department number 5. John Smith does not work in administration, so this does not make sense. So this is what we call a useless tuple or a dangling tuple, or it's kind of a noise that comes as a result of the Cartesian product. And the reason being that these two tables, employee and department, are combined, but there is no filtering involved. There is no specification that the department numbers have to match. So without that, it's going to result in a Cartesian product in all possible rows from the two tables. So if that's the case, if it's resulting in all possible rows, why is it important? A Cartesian product results in a new table with all possible combinations. The operation is very important for any relational database with more than one relation. Why? Because it allows us to process the relation among different relations. So the relationship among the relations, if there are two tables, it allows us to make a relationship between these two tables. While the Cartesian product used simply may result in a lot of useless data, however, as we shall see in the next few slides, we can always add filtering to it and we can make a sense of it. Without the Cartesian product, it will not be possible to combine data from different tables. Then every data either has to be repeated in a different table, or you have bits and pieces of the data, one in the first table, one in the second table, but you don't have a complete picture. So that is why it is important. So it is used to compare rows of one table with another, whether they are common or with additional rows from R1 to R2 or from R2 to R1. And how do we use it? We use it using the Cartesian product followed by filtering. So we'll see all these things in a detail in the next few slides. So let's look at this example. We have the same example, employee and department. This is the Cartesian product just like we had before. However, now what we have done is we have added a filter. That filter is that the department number or the D number from employee, which is this one, must match the department number or D number from department, which is this one. So these two will have to match. So because these two will have to match, we don't have the case where 5 is matching with 4. So this is no longer going to be possible. So once you do this, you see that John Smith, that department number 5 matches with 5, and you have research here. You don't see John Smith with administration any longer. The reason being because now you have added this filter. However, let me emphasize here that because these two have different names, but even if they had a similar name, they are still going to be repeated. since the degree of a Cartesian product is 1, 2, 3, 4, so 4 columns here and 1, 2 columns here. So there's going to be 6 columns, even if this was also called D number. Even then we are going to have a repetition of this. If you want to avoid that, you have to use the projection operator. So what is the join? The join is exactly what we just did. So it's used as a Cartesian product followed by a filter. However, here we did the Cartesian product separately and applied the filter separately. In the case of a join, you use a single operator to perform both these operations. So the join operator is usually denoted by this symbol, is used to combine tuples from two relations in a single relation, provided that they satisfy certain conditions. What are those conditions? Those are the equality or less than equal to greater than. You can use different operators where the common attribute, the values of the common attributes are being matched. So a join of two tables is a Cartesian product followed by a selection operator like we just saw. So if one straightforwardly implements a join without any select, the Cartesian product can be very huge. So we discussed this in the class that, figuring out which one to filter first is important, because otherwise you have to first make the Cartesian product and then use the filter operator. So even though they are going to result in the same thing, using a join or using a Cartesian product followed by a filter, the second option may be very costly, and the reason being that the Cartesian product itself is going to be a huge table, and even though that you are going to filter it at the end, the intermediate table, the Cartesian product between the two tables, is going to be quite large, and this may be so big that it will not even fit in the main memory. And even if it fits in the main memory, you have issues regarding the time constraint or the computational complexity of that. So for this we have the join operator. So the join operator will figure out what to do first, the filtering first and then the Cartesian product, or the other way around. Joins are there are two types of joins, inner joins and outer joins. So we'll look into both of these joins in the next slides. So this is the example of a join. So instead of using the Cartesian product followed by the filter, what you do is you simply write employee, department, the join symbol and the constraint. So these two, this one and this one, they're going to result in the same value. They're all going to result in this table. However, the way they are being dealt with internally may be quite different. This will be quite expensive because you're making the Cartesian product first. This may not be that expensive because you are doing a search operation. You take the first department number over here, number 5, you search through this. So you have a matching over here, then you take this row, and you combine with this row, and there is no other one, so you skip the rest. Then you take the second one and then you match again. You again find another matching, you take this row and again combine it with this one. So you have the second value and so on. So in this case, you are not making the Cartesian product, you are using a search operation, the first row and then you search, and then the second row and then you search. So this may result in less computation. So less computation as compared to this one. So to further illustrate join, suppose we want to retrieve the name of the manager of each department. So if you want to retrieve the name of the manager, if these are the two employees, so you have this table and this table. So to get the manager's name, we need to combine each department row with the employee row whose SSN value matches the manager SSN. So what's matching between? You have the department name, the department number. So this, the social security number of the employee has to match with the social security number of the manager, because the manager is nothing but one of the employees. So to make this, you have to make this matching. Otherwise, for every person you are going to have all possible managers, and under every manager you are going to have all the employees, which is the classic definition of the Cartesian product. So to get this kind of results, it's important to make a join operator. So in this case, what we did was we had the department and we had the employee table. So we have the employee table over here and we have the department table over here. So we made a join operator, and with the join you also write the condition that is necessary. So it's important to note that the condition has to be specified. Even if the numbers were the same, it's not going to automatically assume that you are making a join on this. If you don't write this condition, you are going to end up with a Cartesian product. So you can have this, and the intermediate value is going to be stored in department manager. So since the question was get the manager's name, so we are only interested in the name. So we are going to write the department name, first name, last name and first name of this temporary or intermediate data. So this is going to give us the final result. We could have combined them into a single. We can just have written this operator over here. So you could have written pi and all these things, all these three values we could have written here over with this and make a single statement out of it. So as we discussed, there are two types of join, the inner join and the outer join. So let's look at these two in details. We are going to look at the inner join in this lecture, and maybe the outer join we'll look in the next lecture, because they're not so simple in the sense that the inner join are further classified into three types of join, and the same goes for the outer join. It also has different kinds of outer joins. So let's look at what is the inner join first. The inner join selects all rows from both tables as long as there is a match between the columns in both tables. So to make an inner join, you have to have a match between both tables. In other words, only those values, only those rows will be included that have a match. So in an inner join, for instance, if you use this is the common part. So this is the part that will be denoted, that will result from the inner join operation. So this is, as we discussed, this is how we write the inner join, and is the same as using the Cartesian product followed by the condition. The inner join keyword select all rows from both tables as long as there is a match between them. So if there are rows listed in table 1, if there are rows listed in table 1, so maybe the rows exist over here that do not match in table 2, so does not match, this is not part of table 2, is only part of table 1, these rows will not be listed. So there is no way using an inner join I can have this row be included in the result. As we will see in the next lecture, this is possible with outer joins. So that's what differentiates inner join and outer join. Inner join means only the part that is common that will be reflected in the resulting table. However, even for the inner joins, as I said, we have three different types of joins. So the first join is the theta join, the second is the equi-join, and the third is the natural join. So to understand the inner join, as we said in the last slide, we are going to have to find matching rows. So matching rows, if this is the customer table and this is the job table, if you have Brian over here and the customer ID is 1 and here the customer ID is 1, so you are going to have to match this customer ID with this customer ID. So you cannot, if Mike is here, has a customer ID of 6. Now customer ID of 6 does not exist in this job table. It means Mike will not be included in this resulting table. Similarly here, Dilbert Incorporated has a customer ID number 9, but that customer does not exist over here. It means that Dilbert Incorporated will not be included in this resulting table. So neither Mike nor Dilbert Incorporated will be included in this resulting table. So that's the inner join. Now let's look at the three categories of the inner join. The first one is the theta join. So let's try to make an example of what is a theta join. So for this I am going to take an example. So let's say we have a hospital. So we have a table corresponding to hospitals. We have the name, we have the location of the hospital, we have the size of perhaps the number of beds and the category, what category this hospital is. So we can make a table like this. And we can fill it with values. So for instance, first hospital, we have the Shifa hospital. It's located in I8. I'm going to assume it's going to have 500 beds. I don't know, but we're going to just assume that. And it's a full-fledged or a complete hospital. So the category, I can label it as full. It has every facility, maybe medium and low, depending on what type of facilities are available there. So the next one is maybe Qaid-e-Azam International Hospital. So QIH, this is located in, I think it is H13. Assume it has 400 beds, and this is also a full hospital. And then we have PIMS, which is in G8. It has maybe 1000 beds, and this is also a full hospital. Next, I am going to look at maybe schools. So schools, I have the name of the school, and I have the location of the school, and then I have the level to which they teach, whether it's just primary, secondary, or it goes much higher. So let's take an example here. Let's have maybe Roots International. This is location. I'm just going to assume all this data. So at the primary level, and then I have this OPF. This is located in F8, and this has a secondary level. So what we are trying to do with this example, we're trying to explain what is a theta join. So to explain what is a theta join is, let me assume a query. So let the query be find all hospitals within 5 kilometers of a school. So the query is that I have to find all hospitals that are located within 5 kilometers of a school. How do I do that? The first thing is you are going to look at, okay, what is common between them, and the one thing that's common between them is location. However, these have different locations and these have different locations. So maybe I can use some of the built-in functions. For instance, I can say, okay, I'm going to make hospitals. So I have hospitals over here, and I'm going to use the join operator. This is tricky to draw. So maybe I use the distance function. So I use the distance, and then I have h dot location. So location of this h hospitals, and s dot location. This is less than 5. So hospitals join operation, this is the condition, and join with what? Join with schools. So these are the two tables. This is the first table, this is the second table, this is the first table, and this is the join condition. So once I have this, I can just, maybe I want find all hospital, I just want the name of that hospital. So I'm just going to write this and project the name. So this is going to give me the name of all hospitals whose distance is less than 5. So I'm making a join between these two tables based on location, and since there is no direct match, I am using the distance function such that the distance between these two is less than 5 kilometers. If I were to write an SQL query for that, this would be so select distinct h dot name well, we'll assume they are all small cases, so I'm not going to bother with the capital because it's hard enough to write with this. From hospitals H and schools S, and then in the where condition we'll have where distance, so H dot location and S dot location, this is less than 5. So the theta join, the thing that distinguishes a theta join is that it is able to handle this kind of things: less than, greater than, not equal to. In the examples we saw before, we used to have a direct matching. So if this was a social security number, we need to have a direct map with the social security number. In the case of a theta join, it allows for these kind of operations: less than equal to, greater than equal to, not equal to. Such kind of operators are now allowed, and this is still an inner join because you cannot have a row which is not common between these two to appear in the resultant. So in this case, commonality means it has to be within this distance, the distance of 5 kilometers. So this is the example of a theta join. So we have another example over here. So this one is for the greater than or equal to. So if we have cars and we have boats, so car A, car B and car C is the prices, and then we have the boat model, and then we have the prices. So we are saying that car joined with boat such that car price is greater than or equal to boat price. So we are going to have all the cars and all the boats such that the price of the car is greater than that of the boat. So we see in this case, this is 20,000 and this is 10,000. In this case, 30,000, 10,000, 50,000, 10,000 and 50,000, 40,000. So in all cases, the price of the car is greater than that of the boat. So this is how you are going to represent it, and this is the corresponding SQL that gives you this. So that was the theta join. Next we can look at the Equi-Join. The Equi-Join is very similar to the theta join, except that in this case only the equivalent operator is usable. Others are not allowed. So in this case I am going to write, for instance, I am going to make student, and here I am going to write a shorter one. So student ID here, and we have name here, and then maybe class ID over here. So if you can make this table, so maybe I have an ID of 101, and here I have 0, and here I have 10, and then 102, and here I have Ali, and there I have 20. So this is my student table, and if we look at the class table, so in this case I have simply ID, and I have the subject. So let's say ID number 10 is, if you belong to class number 10, you are taught math, and if you belong to class number 10, you are also taught English, and if you belong to class number 20, you are taught, for instance, AI. So if I make an Equi-Join, so the Equi-Join will be student, and I'm going to make a join with class. Now the nature of the join is going to be, so this is an inner join, so I'm going to write S dot SID is equal to C dot id. So you notice that we have the equality operator over here. There is no less than or greater than operator. So the resulting table is going to give me, so I have SID, I have name, I have CID, I have ID, and then I have the subject. Remember we said that the degree of the two tables are simply added. So here we are going to have 101 and here and 10 math and 101 here 10 and English, and then 102 Ali, 20 and AI. So in this case what we have seen is that the equality operator is used and only the matching values are encoded in the new table. So this is the resulting table. So this is the result of whatever operation you have done. And in case if I am using the SQL, it's simply going to be maybe select asterisk from student S, class C, so where S dot SID is equal to C dot there is no, so C dot ID. Write it again, C dot ID. So this is the equivalent SQL operator. So in this case this is an Equi-Join. Equi-Joins means there cannot be a less than or greater than symbol, and this is an example of the Equi-Join. So we have the employee over here and then we have department over here, and if you're using the Equi-Join, then this department ID has to match perfectly with this department ID. Next is the natural join. In the natural join, what happens is that, note that the previous two we had matching columns or in both cases. However, the natural join does not use any comparison operator. It does not concatenate the way a Cartesian product does. We can perform a natural join only if there is at least one common attribute that exists between the two relations. In addition, the attribute must have the same name and the same domain. It means the name of the column has to be the same, and the domain, the possible values that the column can take, that also has to be the same. So a join that projects out one of the matching columns is known as a natural join. In this case we are not giving the filter. So to look at the natural join, I'm going to have another, so if I have courses over here and maybe I have course ID and then I have the course and then I have a department. So for course ID maybe I have CS 101. So this is Introduction to Computing and Programming, this is offered by the CS faculty, and then I can have maybe ME 101. This is Engineering Workshop offered by ME, and then maybe MT 101, and this is Calculus 1, so Calculus offered by ES. So this is the courses table, and similarly I can have a head of department, who is the HOD of which department. So in this case I am going to have my departments and the head. So this is for CS we have Dr. Ahmed. For ME we have Dr. Sarwat Ahmed, and for ES we have Dr. Nissan. So if I'm using these two tables, and I make a natural join between them. So I make a natural join. I say courses natural join with HOD, and see that I don't write any condition or any filter over here. There is no matching. Courses.cid is equal to HOD. No, there is nothing matching. Or courses.department equal to HOD.department. No, that's not the case. I simply write courses join with HOD, and this should give me department and course ID, and then we have course and head. So it's going to give me something like that. So CS 101, the department is, if I can go to the eraser and erase this part. Okay. So the department is CS, the course is 101. So CS 101, the course is Introduction to Computing and Programming, and the head is Ahmed. So again we move on to the next course, and so for the next course we have ME department, and the course is ME 101, and this is Engineering Workshop and Dr. Sarwat Ahmed. And then we have ES, and this is MT 101, and this is Calculus, and we have Dr. Nissan. So you see that we have all the resulting values, but there was no filter applied over here, and also that the department on which the join is made automatically is listed first. So in this case, department here and department DEPT, the values, the name is the same, and also the domain is the same. So the name over here is the same as this name, and the domain here is the same as this domain. So automatically it's going to form the join on these two columns in the two departments. So this is the third kind of the inner join, which is called the natural join. So just to recap, we looked at three joins. An inner join is the join between two tables based on the rows they have in common. There are three types of inner joins. The first one was the theta join. In the theta join, what we had is we had values in which we can look at less than, greater than, or equal to. So the values between the columns don't have to match. In the second one, the Equi-Join, the values have to match. For instance, the social security ID, or the student ID here and the class ID. So these two matched. And in the third case, in the natural join, we are not going to specify anything, but it's going to figure out what the common column is, and that is based on the name and the domain, and then it's going to perform the join. So these are the three types of inner join. In the next lecture, we are going to look at the outer joins. So I hope you enjoyed this lecture, and if there's any question, you can either email me or ask me during the interactive session that we'll have on MS Teams. So with that, thank you.